So today I want to spend a bit of time demystifying Euler's formula. Okay, so the first thing I want to demystify is how to pronounce this name, because a lot of people I notice, even educated people, pronounce this Euler, and it looks like it should be pronounced like that, but in fact it is pronounced Euler. Okay, so here is a website that does pronunciation. This is the pronunciation of Euler, and it sounds like this.
Euler, Euler, Euler.
Okay, so I think it's important to say people's names correctly. I don't always get it right, but this is an easy one to fix. This is pronounced Euler. So this is what Euler's formula looks like. It is generalized as e to the I times theta, where theta is an angle, is equal to cosine of theta plus I sine of theta. There's also something that's often referred to as Euler's identity, which is e to the I times pi plus 1 equals 0, or sometimes they say e to the I times pi is equal to -1. And this bothers me. It bothers me that they're referring to this as Euler's identity, because identities to me usually equal to 1 or something like that. And so because this equals to 0, I'm not sure why they're calling it an identity, or because it's equal to -1, this is actually e to the I times pi is equal to -1. -1 is also not an identity in the sense of the definition of the word identity. Okay, so I prefer the formula e to the I times 2 pi is equal to 1. Okay, so I is the identity of the imaginary numbers. 2 pi is equal to exactly 1 cycle. So e to the I times 2 pi is equal to 1. And this is also equal to e to the 0. So e to the 0 is equal to e to the I times 2 pi, which is equal to 1. So it would have made more sense to me if they had called this Euler's identity. I'm not sure why they did this. This does not correspond to an identity in my opinion. So I prefer this one. This is actually very useful because this is equal to 1 cycle. So here is the map that I showed you a while ago in my community section, and it shows on the left half it shows the square root of -1, and on the right half it shows you the Euler's formula. Okay, so here we have the square root of -1 is equal to I n minus I, and I n minus I under the hood is equal to these two square matrices, these 2 by 2 matrices. And as we know from studying I, that I corresponds to a 90-degree rotation in the complex plane. Okay, so these two matrices are actually transformation matrices, and they correspond to 90-degree rotations. And so in the previous video, I asked the question why. And the reason why is because under the hood of this is this matrix here, and under the hood of this is this matrix here. And so you can see that this matrix is the cos of 90 on the forward diagonal, which is 0, okay, in both these cases, and the sine of 90 is equal to 1. So here you have positive sine of 90 is +1, negative sine of 90 is -1, and the complex conjugate of that is here. This solves the mystery of why positive I does a counterclockwise 90-degree rotation in the complex plane. Okay, and what I'm going to show you shortly is that the complex plane is just the Cartesian coordinate system. There's no difference. There's no reason to invoke something new here. But because they didn't completely understand imaginary numbers, in my opinion, they had to invent something like the complex plane, which is literally no different than the Cartesian coordinate system. And on the right here, we have Euler's formula right here, which is the cos of theta plus I sine theta, which I showed you in the previous slide. let's see if I can get this up here in this here. Okay, so here we have the cosine theta plus I sine theta, and here we have it written in exponential format. Now this can be further derived from the formula E equal to the square root of minus 1 times theta. So on the left here we have the square root of minus 1, and on the right here we have E to the square root of minus 1 times theta. Okay, so as we know, the square root of 1 is I and minus I. So this formula here, E to the square root of minus 1 times theta, has two solutions. Okay, it's got E to the I times theta and E to the minus I times theta. And E to the I times theta is equal to cos theta plus I sine theta, and E to the minus I times theta is equal to cos theta minus I sine theta. Okay, and then this further, so under the hood of all of this on this branch here is this matrix here. Okay, so here we have the cos of theta on the forward diagonal and the sine of theta on the backward diagonal, and the cos of theta is the same sense. So if the upper left is positive, the lower right is positive, and if the upper left is negative, then the lower right is negative. And we'll talk about this in the next slide. I'll give you more details on this. And so on the backward diagonal, you have the sine of theta, where you have the, if it's positive here, it's a negative here, and if it's negative here, it's positive here. Okay, so these are the two matrices under the hood of E to the square root of minus 1 times theta, which is equal to E to the I, or minus I of theta, leading to Euler's two formulas with the plus sign and a minus sign, and then these two matrices here. And technically, we could actually remove the negative signs here because I didn't write plus or minus in front of this cosine here. Okay, so we will deal with that in the next slide. But before we do that, I just want to point out in this picture here that everything on the left here is basically hard-coded to 90 degrees. So the theta of this formula is hard-coded to 90 degrees. And so we have the cosine of 90 degrees, which is 0, which is why I put zeros here. And you have the sine of 90 degrees, which is 1, which is why I put 1s here. Okay, so this is hard-coded to 90 degrees, and this is the generalized formula that you would use to implement the rotation of any angle. So next, what I want to do is I want to have a closer look at this. Okay, so this is sort of a generalization of Euler's formula where we get both the positive and negative solutions of I, but there is still something missing in this formula here to be further generalized, and that's where this slide comes in. Okay, so this is a slide that I also put up on my community section, and so I'd like to explain this further. So here we have e to the power of the square root of positive 1 and times the square root of negative 1 times theta. Okay, so this is the complete, if you're going to call it Euler's formula, but you know, Euler didn't write this, so maybe you want to call it Fractal Woman's formula. I don't like naming things after people, so you don't have to do that. I'm not sure what to call this other than because it's commonly called Euler's formula. This is a further generalization of Euler's formula, which has 4 solutions, and this is where the positive and negative of the cosine come in. Okay, so this leads to 4 Euler formulas. There's plus cos plus I sine, there's plus cos minus I sine of theta, there's minus cos of theta plus I sine of theta, and minus cos of theta minus I sine of theta. So these are the 4 matrices corresponding to these 4 solutions, or 4 roots, I guess. No, they're basically solutions to this formula right here, which is complete. So this contains both the real numbers and the imaginary numbers, and the real numbers are correspond to the forward diagonal cosine terms, and the imaginary component, the square root of -1, corresponds to the backward diagonal sine terms, okay? So the reason I think this is so important, okay, is because this formula, okay, variations on this formula are used everywhere in theoretical physics. It's used in electromagnetism. It's used in relativity. It's used in light theory. It's used in like the radar handbook. You do not see Maxwell's equations in the radar handbook. What you see are variations on this formula. Okay, variations on Euler's formula. Okay, so in my opinion, since this is used everywhere, it's used everywhere, okay? And I also use it everywhere. I use it in all kinds of places in my research. And so basically what I'm trying to do is trying to take all this craziness, okay, I'm trying to take all this craziness and say, you can do just almost everything with this, okay? You can do almost everything using this 2x2 matrix. Sometimes it's a point, sometimes it's a translation. A point and a translation is basically the same thing. And sometimes it's a rotation, okay? And so what I'm trying to get to, and I think the point I'm trying to make here is that a lot of people are, trying to tell me, oh, you should use the language of vectors and you should do this and you should do that. And I don't think they understand. I don't think you understand what I'm trying to do. I'm trying to get to the creation process of the universe, okay? So the language of algebra is the language of man, okay, the language of humans, okay? Calculus is the language of man, the language of humans. This is the language you need to describe the universe that already exists, okay? What I'm trying to get to is I'm trying to find the universe, how the universe is created. I'm looking for God's math, if you want to say that. I'm looking for the universal math that can be used everywhere, that you find everywhere. And this is the one. This is what you find everywhere. And so this is the math that I use to do all my torus. So a lot of people out there saying, oh, the universe is a torus, particles are toruses. Well, you can use these formulas to generate all the toruses, okay? And so this is the language of the torus. Here are a bunch of torus knots that I generated using my software, and you only need to use these formulas here, okay? Those matrices. I can do everything using these 2x2 matrices. Okay, so these are all my torus generations. Here is a fractal coil that I generated, which is for sale on OpenSea if you want to buy this fractal coil. I generated that using only this formula, and it turned out to be quite simple. When I got the code, I got some code from Bob Greener to generate this torus structure, this fractal coil, and I rewrote it. I wanted to see if I could rewrite it using this, and I was easily able to do it. And this is the first iteration, this is the second iteration, and this is the third iteration. So this is basically, you create a coil, and then you spin that coil on another coil, and then you spin this coil on another coil, and then you spin this coil on another coil. Okay, and all I needed to do was use this formula, only sometimes I would have to replace the x and the y with the x and the z, or the y and z, depending on which orientation I was drawing these coils, okay? So I also use this formula to do a Yanel-Dinyu's ether circulation model, okay? So I'm also able to use these matrices directly to generate these, what Yanel-Dinyu refers to as the creation, this is the creation of electric field, okay? And so I called it the ether circulation model, but it came from Yanel-Dinyu. I want to make sure that it is clear that he came up with this concept and that I just animated it with my software using these matrices. Okay, so here's another view of that. Here is another view, a close-up view, which I thought looked really cool. And so this is on a linear wire. These were all on the linear wire, and this is on a circular wire. And of course, I can generate the circular wire using these matrices as well as all of the dynamics. So this, I was able to use that kind of math to generate what a magnetic field would look like around a circular wire with current flowing through it. Okay, the important part is that current has to be flowing through the wire. Okay, so here's another circular wire, and I'm showing I have circular motion going along these tubes, and this also creates circular motion. And anything that where you have circular motion, you can use these formulas for. Okay. I was also able to use them to do my helix wave interference animations, which I gave you the code for. Okay, and hopefully some of you had time to play around with that. Okay, so here's a few examples of the helix wave interference. Okay, and that these were all generated using basically this right here, this formula, the circular motion, the Euler's formula. This is basically Euler's formula under the hood in 2x2 matrix form. And so, and the most important one, this is the one that got me started. Okay, this is the reason I'm doing all this, because I wanted to understand the Mandelbrot set, and I wanted to understand why it looks the way it does. And so this is very, very important to me. Okay, the whole reason I even started investigating the universe and how it works and trying to study electromagnetism, etc., is because of the Mandelbrot set. Okay, so this particular fractal, again, what I said earlier is what I'm looking for is the creation process. Okay, so for the creation process, see, imagine I'm God and I'm sitting in the middle of, the universe, or there's no universe doesn't even exist yet. And how do I create a universe? How do I create an infinitely complex universe using the least amount of math possible? Okay, and that's this right here. Okay, the 2x2 matrix, this 2x2 matrix where you have the real on the forward diagonal and the imaginary on the backward diagonal, and the real has the same sense and the imaginary has the opposite sense. That's all I need to create this. Okay, so I'm going to get into this in a little bit more detail, but I just wanted to show you the motivation for what I'm doing. I'm looking for the creation process. A lot of people say God does not do math, but if God did math, then this would be all that God would need to create a universe. Okay, calculus is what you need after the universe is created to describe what you're seeing. Calculus is the language of change, and without change we wouldn't need calculus. Okay, calculus is the language of change, and calculus is what you use after you do the experiment to analyze the experiment. Okay, algebra is also the language of man. Algebra is the language used to describe things, to describe how things behave. It is a symbolic language that is compressed. Okay, so let's go back to this right here. Okay, so let's actually go to this right here. So this would be an algebraic expression. This is the 2x2 matrix compressed to this, and this is this compressed to this. So the purpose of symbolic language is so that you don't have to write 2x2 matrices in your paper. Okay, it would look ugly to put 2x2 matrices into a paper, and so it's much easier to write either this or this. And so that's basically, algebra is just a way of symbolically representing what actually gets implemented in the computer, which in this case is, in all the cases of my code that I've written, right, is the 2x2 matrix. Okay, so this is what I implement on the computer to create all these things. I'm creating these things, okay, and I'm not analyzing them, I'm just creating them. And so it is my opinion that if God did do math, that God would be using something like this. So not this, okay, so this is the math that human beings use to analyze the universe after it was created, okay? To analyze an experiment after the experiment is done. Okay, so I'm not talking about this. Okay, so we're going to erase the blackboard, and I'm going to put this on the blackboard. So this is what I'm talking about here. Okay, so this is the math, the only math that you need to do advanced subjects. Okay, all you need to be able to do is add, subtract, and multiply these matrices together, and you can do all of these things that I show you here, as well as the Mandelbrot set. So in the next video, I'm going to get into more details of how this is done. Okay, so I split this video into two because it was taking too long, and so the next video will probably be called Demystifying the Mandelbrot Set, and I'm going to show you how to create the Mandelbrot set with using this matrix here, and only the x and y, the Cartesian coordinate system. So we're going to avoid the topic of the real and imaginary numbers. You don't really need it once you realize that complex numbers are 2 by 2 matrices.